We begin with the hypothesis that adopting probabilistic audiometry by audiologists could involve, for example, exploring standard protocols on virtual patients. One such protocol is the modified Hughston Westlake method, which is still widely used today and relies on testing a finite set of predefined frequencies. By leveraging unused intermediate data, we analyze how this method can actually allow estimation of a continuous audiogram with induced accuracy, and importantly, how Bayesian approach could have achieved the same level of accuracy using less data. Our work focuses on exploring the standard Hughston-Westlake protocol used in tone audiometry through the lens of probabilistic modeling. Specifically, we apply Gaussian process regression within a virtual patient framework. This approach allows us to evaluate the protocol's performance under controlled simulated conditions and to better understand how it may be optimized or adapted using modern probabilistic tools. The ultimate goal is to offer audiologists more flexible and data-efficient methods while maintaining clinical reliability. Our approach is divided in two main steps. First, we simulate auditory responses using the standard Hughson-Westlake protocol. This simulation mimics how a patient would respond to tone stimuli at different frequencies and intensities following the traditional clinical procedure. In the second step, we apply Gaussian process inference to the collected and unused data. This allows us to reconstruct a continuous audiogram by modeling uncertainty and making prediction across the full frequency range, even in regions where no direct measurements were taken. Here we introduce the concept of virtual patient. Each patient is represented by an audiogram which consists of a set of tested frequencies and their corresponding hearing thresholds. For example, we may test 9 different frequencies as shown in the plot on the left. At each frequency, we associate a psychometric function that models the probability of a response based on sound intensity. This function is defined by two parameters, alpha, the hearing threshold, and beta, which controls the slope. Here we present the Hughson-Westlake simulator, which mimics the standard hearing test procedure. We start with a familiarization phase where a comfortable sound level is used to introduce each frequency. The test then follows a staircase method, using up and down steps in intensity based on patients' responses. Frequencies are tested in a specific order, typically from 1 kHz to 8 kHz, then lower frequencies. The process stops when a certain stopping criterion is reached. In this first step, we use the Hughson-Westlake simulator to generate synthetic auditory responses from a virtual patient. The inputs are the patient's audiogram and psychometric function, along with Hughson-Westlake protocol parameters like familiarization levels, step sizes, and the stopping criterion. For each tested intensity, the simulator computes a probability of detection and samples the response using a Bernoulli distribution. The result is a set of probabilistic answers which mimic how a real patient may respond during a hearing test. In this step, I performed a Monte Carlo simulation with 10,000 iterations. For each run, a virtual patient was tested using the Hughson-Westlake simulator. We randomized the responses based on their psychometric profile. At the end, we compute the average estimated thresholds across the simulations, along with their standard deviations, and various other statistical indicators can be calculated. Here we show a table listing the number of yes and no responses collected during the Hughson-Westlake procedure. What's important to note is that the final audiogram only keeps one threshold point per frequency. However, the test actually generates several intermediate responses that are typically discarded. These points, although ignored in the standard protocol, contain valuable information. By leveraging them, we could perform a more continuous and data-rich estimation of the hearing threshold instead of relying on a single binary decision per frequency. In this step, we model a multidimensional perceptual function, specifically an audiogram, using Bayesian active learning BAL with a Gaussian process prior. Starting from binary response data generated by our Hughston Westlake simulator, we compute the predictive distribution at any frequency intensity pair. We then define an acquisition function and select the most informative next stimulus to test, for example, in the sense of mutual information. Finally, we extract the contour which corresponds to the audiogram threshold. In this workflow, we first generate synthetic responses using our Hughston-Westlake simulator across a predefined frequency-intensity grid. We then perform Bayesian active learning iteratively. At each step, we evaluate all unused grid points to identify the single most informative stimulus. We query the simulated listener for a binary response at that point, update our Gaussian process model, and repeat until we reach the maximum number of trials. As a result, we obtain a probabilistic audiogram heat map using only 80 samples, far fewer than the full 155, yielding thresholds at 68 positive responses and 87 negative responses. The next step involves collaborating with audiologists to evaluate, test, refine, and validate the proposed Bayesian Hughston-Westlake protocol. Using virtual patient models, we will simulate diverse hearing profiles and iteratively improve the protocol. By co-constructing with practitioners, we ensure clinical relevance, enhance user experience, and improve early detection of hearing loss. And thank you for your attention.